Good morning, everyone. I am honored to participate in this international academic conference. I am a student from Nanjing University of Aeronautics and Astronautics in China. My contact email is shown in in this picture. During my studies, my research direction was electrochemical manufacturing. The research topic I presented at this meeting is fluid dynamic simulation and experimental study of honeycomb cell structures in electrochemical discharge machining. The content of my report this time is mainly divided into the following four aspects: introduction, research content and methods, research results, conclusions. In the introduction section, I will mainly introduce the application, background, structure, characteristics, materials, and some manufacturing difficulties of honeycomb cell structures, as well as technical characteristics of electric discharge machining. In the research content and methods, I will introduce the honeycomb cell structure, towed electrodes, simulation modeling, simulation parameters, experimental equipment, and experimental parameters used in this study. In the research results, I will provide a comprehensive discussion on the simulation and the experimental results. In the conclusion section, I will provide a comprehensive summary of this study. Firstly, this is the introduction. Honeycomb cell structure is an advanced sealing device used in the aircraft engine compressors and turbine rotors. As shown in Figure 1, the honeycomb cell structure is a hexagonal honeycomb with a core cell length of 0.8 to 1.6 millimeters and a single wall area width of 0.03 to 0.05 millimeters. Due to the high temperature and high pressure working environment of the honeycomb cell structure, the manufacturing materials of the honeycomb cell structure is hastily X, which has high strength and high temperature resistance characteristics. Due to the structural characteristics of honeycomb cell structures and the difficult processing characteristics of the honeycomb X, the current processing methods has many processing defects, such as low processing efficiency, core cell flapping, and collapse. Based on the processing difficulties, this study proposed to use electrochemical discharge machining to process honeycomb cell structures. This method combines electrochemical machining with electric discharge machining. ECDM can switch freely between the three processing states of ECM, EDM, and ECDM as shown in Figure 3. In Figure 4, the initial machining stage is ECM, and there are many bubbles in the machining gap. The bubbles are the insulating medium that induce EDM. When the machining gap is smaller than the discharge gap, ECDM officially starts working. Therefore, ECDM has the advantages of high efficiency, high processing, good service quality. However, there is currently little research on ECDM processing honeycomb cell structures. which is an important reason why this study is worth conducting. The main research of this study is as follows. The simulation of experiment was conducted on the processing of honeycomb cell structures used in ECDM. In the simulation section, 3 different fluid supply methods were designed to analyze the flow field state. In the experiment section, different variables were used to analyze the evolution process of processing morphology and surface quality. The current signals of ECDM was processed to obtain the characteristics of current signals on the different processing states. In Figure 5, the material of honeycomb cell structure is hastily X. In the honeycomb cell structure, the area where 2 core cells are connected is a double wall area, while the area where they are not connected is a single wall area. The torus electrode is made of copper tungsten alloy electrode with a diameter of 20 millimeters and a length of 80 millimeters. In the process of establishing of the simulation modeling, 3 different liquid supply methods were designed, namely front fluid supply in the negative x direction, the rear fluid supply in the positive x-axis direction, and the bilateral fluid supply on both sides. The simulation in figure 6, the simulation model includes a honeycomb cell structure, the rotating wall surface of the torus electrode, the internal and alternate of liquid supply. To simplify the model in the XY plane, it is assumed that the machining gap is always maintained at 0.05 millimeters during the machining process. In figure 7, 5 points are selected at a distance of 0.025 millimeters from the rotating wall within the machining gap to observe the flow field distribution within the machining gap. In order to simplify the simulation process, some assumptions were made to the simulation model. The first is the electrode was continuous and incompressible. The second is the electrode didn't contain solids and bubbles. The third is the effect of temperature was negligible. The flow field satisfied this turbulence model. The mass equation and the momentum equation of the simulation process shown in the figure. The parameter settings for the simulation are shown in Table 1. The total simulation duration is 0.12 seconds, which is exactly the time it takes to rotate one cycle. The experimental equipment for the study is shown in Figure 8, and the machine device can perform X, Y, and Z axis movement as well as Z axis rotational motion. The power supply was powered by a DC power supply. and the current signal is collected by a multi-channel sampling device. The sampling current size is 0 to 2000 ampere, and the sampling frequency is shown in the figure. The surface morphology of the processed surface after the experiment was measured by a super depth of field microscope and a ultra-high range microscope. The experimental parameters are shown in Table 2. Wavelet is the effective method for processing composite electrical signals, which continuously decomposes the original signal to grasp its characteristics, as shown in Figure 9. Wavelet uses functions with fast decay and oscillation as the mother function and obtains wave basis function by scaling and translating the mother function through scaling and translation factors. Limited signals of different energies can be decomposed based on the basic function to meet the requirements of different resolutions. The function of the wavelet is shown in this figure. In this study, the wavelet basis function was chosen as dB3, and the length of the wavelet decomposition was 6. To ensure the reliability of these assay results, the simple point was selected, and after 6 layers of decomposition, the factual sampling frequency of sampled signal was 128. In the experimental results section, it can be found that from the analysis of simulation results that, as shown in Figure 10 and Figure 11, the pressure on a single liquid supply is significantly higher than that on a bilateral liquid supply. There is a significant aid current forming inside the Honeycomb core. Comparing the 3 aid current formula, it can be found that the aid current formula is significantly improved on the bilateral liquid supply. At the intermediate sampling point C, the pressure and the flow rate are both the lowest. After transforming the machine equation of the electrolyte, the rotation equation of the electrolyte is obtained, as shown in this picture. And the eddy current formula in the processing area is further analyzed by the magnitude of vorticity. In figure 12, the vorticity size is significantly smaller when the liquid is supplied from both sides than when it is supplied from one side, indicating that the use of both sides liquid supply can ensure the stability of the flow field and is beneficial for the actual processing. Therefore, in subsequent experiments, a bilateral liquid supply method was adopted. In experimental results, the cut in morphology after processing is shown in Figure 30. The increase in voltage increases the total energy, resulting in deterioration of the cut in morphology. As the electrolyte flow rate increases, the eddy current fermion inside the honeycomb core becomes more severe, leading to an uneven meshing morphology. A lower electrolyte concentration will enhance the EDM effect, leading to a decrease in the amount of molten products removed by the ECM. However, as the concentration increases, the ECM effect on the surface stretching becomes stronger. The surface morphology after the processing is shown in Figure 30 to 60. As the voltage increases, the number of molten product height gradually increased, and the inner wall of the honeycomb cores also gradually becomes thinner. However, an increase in flow rate cannot wash away most of the molten products, but instead enhance the eddy current situation, causing the inner wall of the core become thinner. As the concentration decreased, the amount of molten products increases, and the surface morphology is much worse than that at 1%. The analysis of the processing tips of over corrosion depths and the height of molten products revealed that an increase in voltage leads to an increase in total energy, resulting in an increase in process depths over corrosion depths and height of molten products. However, an increase in flow rate enhances the range of eddy current effect and discharge ablation, leading to an increase in processing depths over corrosion depths and height of molten products. When the concentration is low, the energy of EDM increases. The processing depths and height of molten products is increased. While when the electrolyte concentration is high, the energy of ECM increases, removing molten products but leading to an increase in the depth of over-processing. The signal processed by DWT shows that the voltage at 10 and 50 are relatively stable discharge voltage stages with strong EDM, weak EDM, and ECM signals present. After the electrolyte flow rate increase, more EDM signals appear, indicating that the effect of EDM is enhanced when the electrolyte wash away some of the molten products. As the concentration decreases, the decrease in conductivity leading to an enhanced effect of EDM and a weak effect of ECM. Results in more EDM signals at low concentrations. The last part is the summary of this study as follows. The first is the pressure distribution. The first is the pressure distribution of the flow field showed that the bilateral fluid supply was more uniform, and the gradient of pressure change was small, which can avoid the situation of insufficient supply. The vortex effect observed in the streamlined cloud diagram can lead to the accumulation of electrolytes in the machining gap and the Honeycomb core, which hinders the electrolyte flow. When using bilateral fluid supply, the velocity and the vorticity distribution on both sides were uniform and smaller, and the vortex effect was weaker. The third is the increase in voltage can increase the total energy, thereby enhancing the interaction strength of EDM and ECM. Similarly, an increase in flow rate strengthened the vortex effect and increased the range of EDM and ECM. Therefore, the increase in voltage and flow rate can increase the processing depth, exacerbating the over-corrosion depth and molten product height. The concentration of electrolytes was negatively correlated with electric discharge intensity and frequency. Increasing the concentration reduced the EDM effect while enhancing the ECM effect, thereby increasing the processing depth and over-corrosion depth, but decrease the molten product height. After DWT of current signal, the interference peaks in the original signal can be removed. The results showed that ECDM consists of a stronger EDM signal, a weak EDM signal, and an ECM signal. The appearance frequency of the EDM signals was negatively correlated with voltage and concentration, and positively correlated with electrolyte flow rate. Okay, the above research content is all the content of my report. Thank you, everyone.